Australia is currently experiencing one of its worst droughts on record, with water levels in Warragamba and Nepean dams falling below 50% and the Murray-Darling River running dry. Water is the most important commodity for people, so environmental engineers are constantly looking for ways to improve our access to clean water. Reverse osmosis is currently used in desalination plants around the globe, including Kurnell in Sydney, as another way to provide potable water. The Kurnell plant is used as a backup system for when dam levels drop and is currently turned on. The objectives of this presentation are to discuss whether reverse osmosis provides an efficient and effective method of producing drinking water, while also analysing its overall impact on the environment. Reverse osmosis is a membrane process that produces the highest level of water treatment, utilising a semi-permeable membrane that allows water to pass through while rejecting contaminants. Water is pumped through pipes at 50 to 60 bar pressure, greater than the osmotic pressure, with clean water coming out the other side, as well as brine, which is then disposed of, as shown in the diagram. Seawater consists of 96% water and 2.5% salts, with the remainder being other substances such as organics, bacteria, and other chemicals. Sodium chloride or table salt has the highest concentration. Other common ions are sulfate, magnesium, potassium, and calcium. Reverse osmosis has the ability to remove almost 100% of most common chemicals in seawater, removing 98% of sodium ions. These chemicals are important to remove as they can be harmful to the human body or cause build-up in the pipes. The concentrated brine is simply dumped into the ocean via an ocean outfall system and is at twice the salinity and 1 degree warmer than normal seawater. This impacts the surrounding environment by changing its pH levels, concentration of salt, temperature, dissolved oxygen levels, and so on. Environmental engineers in the US have developed a method to convert brine into sodium hydroxide through nanofiltration and dialysis. This not only protects the ocean life by reducing the amount of brine being disposed, but it improves the effectiveness of desalination. Sodium hydroxide reduces fouling, which decreases the treatment plant's energy consumption. Fouling is the accumulation of materials on the membrane and decreases the effectiveness of reverse osmosis. To maintain the same flow, engineers must increase the energy input, using more electricity. This again increases the toll on the environment and also increases costs. Desalination is energy intensive and also costs more than traditional ways of producing potable water. Hence why Sydney's desalination plant is only a backup to the dams, such as Warragamba. They claim to offset the energy they use by investing in renewable energy. However, they are still using a huge amount of energy, which they don't actually get from renewables. Reverse osmosis has been proven to be a very effective solution for producing drinking water. The desalination process is a good environmental engineering solution. However, it should not be used as a primary source of drinking water due to a number of flaws. Desalination plants are expensive to set up and run, meaning they can only really be used in developed countries. The disposal of brine into the ocean can be very harmful to the local ecology. Although there are ways to reduce the brine and reuse it, it is not energy and cost effective to recycle all of it into a new product. Desalination plants also use a lot of energy and electricity compared to traditional sources of clean water. To conclude, reverse osmosis provides a very effective engineering solution for the production of drinking water. It should be used only as a backup system for situations like we are currently facing, where dams and rivers cannot provide a sufficient water supply. With continued development, reverse osmosis may become the #1 method of sourcing drinking water if engineers are able to reduce its impact on the environment.